Hello, my name is Andy, and I'm with Elite Prep. And today, we're going to be looking over some AP Chemistry questions related to acids and bases. Okay, so let's take a look at question number 1. So here, a student studying the reaction between lactic acid, a weak acid, and sodium hydroxide, a strong base, as represented in the balance equation above. Okay? So here we have our stereotypical acid and base reaction, but we have lactic acid, which is a weak acid. Alright? So we have weak acid here. And then we also have a strong base. Okay? And this is going to be your weak acid and strong base reaction. And as a result, what we get is a weak conjugate base and water. Okay? So that's going to be a weak acid and strong base, acid-base reaction, producing a weak conjugate base and water. Okay? Now, let's look at A. A structural formula of lactic acid is shown in the following diagram. Circle the hydrogen atom that most readily participates in the chemical reaction with sodium hydroxide. Okay, so we have a molecular drawing of our lactic acid drawn for us. Thank you very much, AP Chemistry. And now we have to look at all the hydrogens and see what is the hydrogen that's going to be involved in this acid-base reaction. And we have so many to choose from. 1, 2, 3, 4, 5, 6 hydrogens to choose from. Okay. So what we have to do now is remember to find the hydrogen, okay, that leaves the molecule to form a proton. Okay. You have to find the conjugate base stability. Okay? And conjugate base stability, you have to understand, has 2 main factors. 1, resonance, and 2, electronegativity. Okay? And so now, only this hydrogen, okay, so here is next to 2 very electronegative oxygens. Okay? So that's number 1. So, and then number 2, and here, these 2 bonds could form resonance, right? And so we have this hydrogen as the hydrogen that's most likely to be involved in this acid and base reaction, okay? Conjugate base stability, resonance, and electronegative atoms. Got that? Let's move on. Okay, so now a student is studying the reaction between lactic acid. So same question, right? But now they're saying that a student begins the experiment by dissolving 10.22 grams of sodium hydroxide, yeah? And they give us the molar mass, thank you AP Chemistry, in enough water to produce 500 milliliter solution, okay? And we're supposed to calculate the molarity of this solution, sodium hydroxide, okay? So how do you find the molarity or the concentration? Well, we use this equation. So that's going to be our unit for molarity and concentration. Okay, how to find concentration. And to find concentration, what we have to do is we have the mass, right? So we have to first find number of moles, and also we have to find the number of volume in the solution, right? So let's first find number of moles first. We're given the mass of sodium hydroxide, and we're given the molar mass, right? So to find the number of moles, we divide 10.22 grams by its molar mass. And we end up with number of moles. Now we have to calculate the volume. Well, remember, the volume has to be in liters, as shown here, right? So to produce 500 milliliters is equivalent to what? Exactly. So 500 milliliters is equal to 0.500 liters, okay? So now that we have moles, number of moles of NaOH, and we have the volume of the NaOH, we can find the concentration, and it comes out to be 0.511 molarity. And there we go. That's the answer. And here we want to keep three significant figures because the smallest significant figures is 500 period. Okay, so that should be your answer. Moving on. So now we are given this graph, right? Titration curve, basically. And so the student uses sodium hydroxide solution from part B of Barrett pH meter and 100 milliliter Erlenmeyer flask to titrate a 25 milliliter sample of lactic acid solution. The student's data are shown in the following graphs. Okay, so here what we see is, so let's analyze it, okay? First, we have a weak acid. So it's going to have a low pH, okay? But not too low because it's a weak acid. Then we have, as you continue to add the OH, strong base, hydroxide ions, we're going to have a steady increase in the pH, okay? And then what happens is here, we have an equivalence point in which the number of the weak acid and number of the strong base, number of moles of both, are exactly the same. And at this point, what we have is we only have the conjugate base and water at this point. And past this point, what we have is addition of OH minuses, all right? Past this point, because all the weak acids has been reacted after this point, and therefore we have a increase in the pH, okay? So that's how you read this graph and this curve. And let's continue on. Okay, so now we are to use information in the graph to determine the approximate pKa of lactic acid. Now, remember our Henderson-Heidelberg equation. Now, that sounds familiar, intimidating, but don't worry, this will be given to you in the AP Chemistry formula sheet, okay? But for now, just follow along. Okay, so this is the Henderson-Heidelberg equation, and what we know is that at equivalence point, okay, at equivalence point, we have all of the weak acid, okay, has been converted to weak base, okay, due to the same number of moles of NaOH and reacted with the same moles of the weak acid, yeah. So we only have the weak base here. However, at half equivalence point, okay, which is going to be exactly half of the 16. And what is that, you guys? 16 divided by 2 is 8. Great. So at half equivalence point, what we have is that we have equal amounts of the weak acid and conjugate base, all right? And this is something amazing that happens to the equation, all right? Here we go. So at this point, at half equivalence point, we have the equal amount of the weak acid and conjugate base, all right? And so here, if they're the same, then we have this value becoming 1, right? And log of 1 becomes 0. So you can kind of ignore this, right? Yeah. So once again, the ratio between the weak acid and its conjugate base is 1, and log of 1 is 0, and of course when you either add or subtract by 0, same number, so this one disappears, right? And voila, we have it. At half equivalence point, pH is equal to pKa, all right? And now if you follow along, remember, equivalence point was 16 milliliters, right? So whereas the half equivalence point, it's going to be half of that, which is going to be here, okay? And so now, at this point, the pH is what, you guys? Follow along. Exactly. pH is 4. And pKa then, at this point, yeah, you can find out the pKa, and it's going to be 4. Okay? So remember, pH is equal to pKa at half equals point. Okay? Let's move on. Okay? So this is going to be the last one that we have for this question. Okay? So preceding diagram represents the relative amount of measured species in a sample of the solution in the flask at one point during titration. Okay? And they took out the water molecules, all right? And now we were to draw an X on the preceding titration curve at a point in titration where the reaction mixture will be represented by this diagram, okay? Reaction mixture will be represented by this diagram. So now we have here, let's see. So let's count the number of weak acid we have available, right? So remember, initially we have all weak acid, right? And then at the half equivalence point, we have equal amounts of the weak acid and its conjugate base. And at equivalence point, we no longer have the weak acid, and we only have its conjugate base, right? But here, what we see is that we have more weak acid than its conjugate base, right? So this is going to be before the half equivalence point, okay? And also, right now, we do have some of the conjugate base due to the reaction. So we can safely say that the X mark could be somewhere between 8 milliliters and 2 milliliters, somewhere around here. Okay? Sounds good? And let's justify our answer for number 2. So, for justifying in AP Chemistry, you are not writing an English essay, and it's not an AP Literature class. So, you just have to point out the main facts. So let's actually type it up. So the number of weak acids is greater than the number of its conjugate base. Therefore, this must be before the half equivalence point. Yeah. So there you have it. So for AP Chemistry, many students have difficulty with acid and base questions, but if you think of it in a molecular level, and if you try to think about what exactly is going on in terms of diagrams, then many students can have much easier understanding, and they can apply those concepts to more advanced acid-base questions that you will see on the day of the exam. Thank you so much, and I'll see you next time.